Hello, welcome back students. We are on lesson 3 on hydrometer. Today I want us to look at how can you use the hydrometer to find the relative density of a liquid. Here practically, I have said before, practically if I want to find the relative density of a liquid, I don't have to do any calculation. I will just use the device directly, then take my reading. But here, what about if we want to apply theoretical calculations to this thing? How do I use that? Right? That is what I want us to look at. So this diagram is going to be our reference diagram. So if I want to find the relative density from the definition, we know that the relative density, we know that relative density of any given liquid in terms of density is given by the density of that liquid over the density of water. So here we know that for relative density, water is our reference liquid, right? So if I have this, for example, if I want to measure the relative density of another liquid apart from water, then I have to insert the hydrometer in both. I insert it in the liquid. I will take, let's say after inserting, the depth to which it was sink is LL. Then I'll clean it and I'll come and insert the same hydrometer in another liquid, in water. So let's say because the liquids are different, the hydrometer will not submerge equally. It will submerge differently. So let's assume that the length which it submerged in the water is LW. What do we do here? That is our focus. I want us to derive an expression for that. So how do we start it? How do we start it? Let me call this A. Okay, let me change my pen. I want to use bread for this. Let me call this A and let me call this B. Okay, so what is my focus? I want us to find let's consider figure A. From A, okay, what will be the weight of the hydrometer? The weight of the hydrometer is equal to the weight of the displaced. A is the liquid, another liquid. And what principle is that? I think this one will help me if I can. Yeah, I won't divide my board. So weight of the hydrometer is equal to weight of the displaced liquid. And where did I get this one? That is from law of flotation. Okay. So what do I do? So I can say that, and we already know that this is the same upthrust. So I can say weight of the hydrometer, if it is equal to the weight of the displaced liquid, then this is equal to the mass of the displaced liquid, MD. Let me use MD for mass of the displaced liquid, times G. And this is the same as density of the liquid times volume of the displaced liquid times G. All right. So that is for figure A. And we know that this VD, check the diagram. In terms of cross-sectional area, we are on figure A, okay? So in terms of cross-sectional area and length, I can rewrite this as rho L times area, cross-sectional area of the hydrometer, times LL, all right? Length of the submerged part times G. Let me call this equation 1. So length of the submerged part is the LL. Let's use the same analysis for B. So for B, we can also say that weight of the hydrometer, because it is floating, right, is equal to weight of water. B contains water, right? Water displaced. And this is the same as mass of water displaced times G. And this is the same as density of water, right, times volume of the displaced water times G. Alright, and this can be rewritten as density of water times cross-sectional area of the hydrometer times LS. Here our LS becomes our LW, length of the submerged part in water. So times LW times G. So let me call this equation 2. Now what can we say about equation 1 and equation 2? Don't forget, it is the same hydrometer that we use in A and B. So if A, look at this, A is equation 1 is finding the weight of the hydrometer in A. And equation 2 is also finding the weight of hydrometer in B. Check it. But it's the same hydrometer, so the weight will not change. It's the same weight, all right? So since the same hydrometer is used in both A and B, it implies our equation 1 equals our equation 2. All right? So if equation 1 equals equation 2, then what can we get? This is equation 1 and this is equation 2. So we can say that, okay, rho L V, A times LL times J should be equal to rho W times what? A times LW times J. It's the same hydrometer, so the cross-sectional area will not change, J will not change. And if I am dividing through by A times J, if I divide through by A times J, what do I get? We are going to get rho L times what? LL is equal to rho W times what? LW. Maybe someone is confused. How did it happen? When you divide here by A times J and you divide here by A times J, they will divide and it will go. Okay? That is why I have that. Thank you. So, our focus, don't forget, our focus is that we want to derive the relative density of the liquid. And we know that relative density is density of a liquid over density of water. So here my focus is I want to make rho L over rho W the subject, because if I make it the subject, then that becomes the relative density. So how do we find it? So we have what? How do we get it? So I'll first divide through by, I'll divide here by rho W. I'll divide here by rho W. So the rho W's will divide and will go. And when they leave, what am I going to get? So you can pause it, write it. See, this is going to cancel this, right? So I'll be left with this part. I'll be left with rho L times LL over rho W on the left hand side. So rho L times LL over LW equals what? Rho Check it. Rho W LW over rho W. Rho W. This is what we have. So I just repeated it to avoid trouble, okay? So what do I get? Let me go back and check. Yeah. No, I think I've made a mistake here. It is rho W, rho W, rho W, rho W. So this goes, we'll be left with what? Rho L over rho W times rho L is equal to LW. So how do I get? I need to let this one stand alone. I am making this one the subject. So how do I let this one stand alone? I have to divide through by the L1, which is multiplying. Okay? So let us divide. Dividing through by L1. What do we get? We are going to get rho L over rho W times L over equals LW over L1. So finally, what do we get? We eventually get rho L. Okay, I don't want to go back to the next page and then, so let me get this. I'll get rho L over rho W is equal to LW over L. This is a powerful equation. This is a powerful equation. Now, what does rho is density of a liquid. What does density of the liquid stand for? Density of liquid over density of water. It stands for relative density of the liquid. So I can say relative density of the liquid is equal to LW over LL. So this is a very powerful equation, students. Take note of this equation and take note of this equation as well. So these powerful equations, these two equations are so powerful. We will be using them. All right. So LW, what is LW? LW is the length of the submerged part of the hydrometer in water. Then LL is the length of the submerged part of the hydrometer in another liquid. So in summary, if you have the hydrometer, then I can say density of the liquid over the density of water is equal to what? Length of the submerged part in water, length of the submerged part in liquid. So this is our first equation. Then the second equation, we can say this one stands for RD. So relative density of the liquid which we want to calculate is equal to length of submerged part over length of this. So these are two powerful equations we should take note of. We will be using them in our next lesson. Okay? Thank you very much and see you again in lesson 4.